Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Algorithms Learning. How do artificial brains learn optimization math? It corresponds to one of several short conferences, in which the advances of HI research are presented, on the topic of artificial brains and decision-making artificial intelligence. Lecture edited by Jesus Velasquez Bermudez. The stages of teaching and learning have occurred throughout the entire life of humanity, and they have been its means of development. Starting with human learning, in which humans teach humans, and humanity evolves slowly, this stage begins to change in the middle of the last century. Since the invention of computers, scientists begin the process of giving them the ability to solve real-life problems. This could be called the birth of machine learning, in which humans teach machines by making the algorithms that are the basis of artificial intelligence. This is the era we live in, which has the peculiarity that these algorithms are mass-produced and commercially sold to machine learning users. The next logical step is called by HI algorithm learning. At this stage, machines will learn to create algorithms without human involvement, and algorithms will learn autonomously to improve their behavior. This is a necessary step to arrive at the artificial general intelligence, AGI, the dream of scientists. How do human brains learn? By Donald Hebb. Neurons that fire together, wire together. Donald Olding Hebb, July 22, 1904, August 20, 1985, was a Canadian psychologist who was influential in neuropsychology, where he sought to understand how the function of neurons contributed to psychological processes such as learning. He is best known for his theory of Hebbian learning, which he introduced in his classic work The Organization of Behavior, 1949. Hebb has been described as the father of neuropsychology and neural networks. His views on learning described behavior and thought in terms of brain function, explaining cognitive processes in terms of connections between neuron assemblies. The central concept of Hebb's theory is summed up in the phrase, cells that fire together, wire together. According to this idea, when an A neuron is repeatedly involved in the activation of a B neuron, the synapses between them are strengthened. This principle suggests that the concurrence of neural activity is the basis for learning and memory. Synaptic strengthening: when a presynaptic neuron and a postsynaptic neuron are activated simultaneously, the connections between them are strengthened. Activity-dependent plasticity: the efficiency of synaptic connections is not static but can be modified as a function of neuronal activity. This plasticity is essential for adaptive learning and memory. According to HI, the most important question Hebb solves is learning due to the addition of new cells in the brain? Learning is not about new cells, it is about new connections. Because of the creation of new and more efficient connections in the brain. Experience induces synaptic change facilitates pattern competition, activity, not synaptic change, is sufficient for memory cognition. We define augmented artificial intelligence, AAI, as the creation of artificial intelligence from the neuroscience of human intelligence, integrated with the mathematical laws of smart, physical systems. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. Emphasizing that HI is not an expert in neuroscience, its interpretation of the functioning of the brain is presented. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. Artificial cortex. The neocortex contains millions of neurons that communicate with each other to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. This section is based on the paper, "Why does the neocortex have layers and columns? A theory of learning the 3D structure of the world." Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. In mathematical models, it is common to use a matrix that relates columns with variables and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. Therefore, the learning process of an artificial brain involves increasing the number of connections that are mapped into the artificial cortex. This means larger and/or denser matrices. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. For high cortical connectivity represents a map of how neurons in the brain are linked. All the cerebral cortex produces the large neural network of the brain, and other important organs. Artificial hypothalamus. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. The artificial hypothalamus emulates the human hypothalamus as a computer-distributed processor that solves multiple problems, representing the holistic model of an organization. This process can be called autonomous real-time distributed optimization. The optimization methodologies to be used are selected by the artificial hypothalamus. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. The diagram presents the hierarchical structure of decomposition and partition of an oil company. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. The representation is based on atoms, or neurons, which is normally a tuple composed of time and an organization asset, where the assets are connected forming a network, in which each of them represents a dynamic vision of the neuron. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition, developed by Van Roy, makes it possible to establish complex optimization processes, in which multiple methodologies are used on a large scale. This allows the problems to be adjusted to the most convenient methodology for the solution of each subproblem. This implies a universal conversation between multiple algorithms, built with different methodologies. It also frees the decomposed problem from bidimensional hierarchical tree-like structures, enabling horizontal communications between subproblems. From the point of view of multi-layer structures, cross-decomposition results in the exchange of information between multiple layers, of different columns, like the actual structure of the human neocortex. As in the human cortex, lateral connections between columns allow the network to solve problems more quickly, based on partial knowledge of adjacent columns. Cross-decomposition can be said to be a smarter scheme, due to the creation of new and more efficient connections in the artificial brain. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. To handle the concept of mathematical intelligence, Hai developed the concepts of mathematical artificial neural nets, MANN, which complement the concepts of artificial neural networks, ANN. Hai developed a theory for building networks of artificial neurons specially built to integrate the artificial brain and fit into the structures of the artificial cortex. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. This new type of neuron will be called mathematical artificial neuron. Its name was derived from the fact that the neuron is built, based on mathematical models that represent a system, and that it contains logical or intuitive elements. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. When the atomization of the system is pushed to the limit, the atom of the system will be the operation of the system over a period of the planning horizon, under a specific random scenario. Artificial hippocampus, a mathematical model's expert system. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. The operation of the artificial hippocampus is presented as an expert system that must store two types of knowledge. Formulation: the components of mathematical models, and historical data of the results generated solving the mathematical problems, using large-scale optimization methodologies, This information is used as starting point in future uses of mathematical models to support decision-making. The hippocampus. Storage structures and processes from the decision-making that must be faced permanently. The artificial hippocampus is based on the mathematical synthesis of the information generated by algorithms and problem-solving processes, to use it in new runs of these algorithms to speed up the problem solution in real time. Artificial hippocampus store, like in the humans, the experience, and the knowledge acquired over time. It could be said that, to support decision-making, the artificial hippocampus stores historical information related to the models formulated and that work correctly, and the runs made with a certain model, in such a way to be able to use this information in new runs. The first case has already been analyzed throughout this presentation. The information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. Artificial hippocampus, a mathematical models expert system. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them, remember. Algorithms that learn during the solution process. While mathematical models on digital computers, and the data storage disks, date back many years, more than 60 years, and despite the Industrial Revolution 4.0, how to run a model, it does not seem to have evolved. The normal process is: the model is thinking monolithically. A high-performance solver is selected to solve the problem, and the results are post-processed, and the results of the models are stored, with administrative purposes. Usually, in the next run, the model starts from scratch, ignoring the past, that is, it has no memory. In some cases, it is heated from a starting point provided by the last run, presumably the last optimal solution, or a point that ensures feasibility. However, an artificial hippocampus, designed for the artificial brain, can take advantage of a lot of information produced within a run, and during the history of all runs. Two examples will be briefly presented: handling of Bender's theory, and generation of convex hull. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Artificial brains are based on multi-problem mathematical models, the solution of which must be addressed with large-scale optimization methodologies. As an example, we will analyze the construction of an artificial hippocampus using Bender's partition theory. Benders divides the model of a system into two: a coordination problem and a dependent problem. To solve the model, a conversation is established in the two problems. The solution of the model involves a conversation between the two math problems, or agents. The coordinator, over y, variables controlled by the board of directors, and the subproblem, over x, variables that are controlled by the production manager, and that depend on the decisions of the board of directors. In its original form, Bender's algorithm involves a sequential conversation between the coordination problem and the slave problem. In non-mathematical terms, the board of directors sends a set of technical decisions to the production manager to assess their impact, that is, the marginal costs and benefits, for all resources, which are the economic indicators of the board's decisions. With this information, the board analyzes the optimality of its decisions and, if not, sends a new proposal. The process involves the partition of the monolithic model into two smaller problems, the coordinator and the subproblem. This will reduce memory and processing time requirements. This division does not produce knowledge to solve the model. It simply produces two problems, which only together can solve the model. To solve the problem, Benders devised an algorithm in which the coordinator captures the information provided by the subproblem, through constraints, called cutting planes, in red, in such a way that, under certain mathematical conditions, the algorithm converges to the optimal solution. At the time of convergence, the cutting planes represent everything that the coordinator learned from the subproblem, and the subproblem is not necessary. If only certain parameters change, the next time the issue runs, the subproblem may not be necessary. Like any optimization problem, this one has a matrix formulation that High has associated with the artificial cortex. The problem is divided into the coordinator, psi-bt, and the slave, sp-bt, each with its own connection network in the artificial cortex. Splitting the problem is splitting its matrices. When starting the optimization process, there are no cutting planes and therefore this part of the problem does not exist in the artificial cortex. Psi-bt includes two types of cuts that limit the feasibility zone of Y, in other words, indicate decisions that cannot be made by the CEO. The first type, that we call optimality cutting planes because the cut eliminates values of board decisions, that can't be optimal, every time the slave problem is solved, until the optimum, or until a nearby feasible solution, a cut of this type is generated. The second type, the feasibility cutting planes restricts the feasible zone of board decisions to maintain feasible solutions in the production problem. Every time the slave problem produces an unfeasible solution, a cut of this type is generated. The second type, the feasibility cutting planes restricts the feasible zone of board decisions to maintain feasible solutions in the production problem. Every time the slave problem produces an unfeasible solution, a cut of this type is generated. The coordinator's solution implies a learning process in the algorithm, which is configured with the minimal connectivity. As iterations occur, the number of connections in the artificial cortex increases, which corresponds to the learning of the algorithm, that is part of the artificial brain. If the dual variables of the subproblem of each iteration have been stored in the artificial hippocampus, when the process stops, and starts again, including the previous cutting planes, everything will be faster in the second run, implying that the brain has learned from one run to the next. As the process progresses, the coordination algorithm increases the size of the array, which is a learning process, which coincides with Hebb's postulates. On the other hand, the subproblem algorithm keeps its matrix equal in size, which means that it retains its knowledge and that the learning process is concentrated at the highest and most powerful level. When the system is atomized and represented by mathematical artificial neural networks, all the problems that make up parts of the connectivity described by the cortical envelope simultaneously become coordinators and slaves, except for those in the top row, which are only coordinators, and those in the bottom row which are only slaves. In this way, the algorithm has a dynamic memory during the process, which learns during the solution of the problem, just as it happens with the human brain. For example, a basic artificial hippocampus can be constructed using Bender's partition theory, which can be interpreted as: the general problem is divided into two complementary subproblems, an experimenter, that makes decisions in real, or in simulated, environments, and that send the results to the higher level, and an information manager, that stores the results, sent as primal and dual variables. When it is required to make a real decision, or to perform an experiment, the information manager processes the stored data to determine two zones with respect to decisions, a desirable zone and a non-desirable, or utopian, zone. Mathematically, this is done by generating cutting planes and incorporating them as part of the information to be processed. The experimenter receives the information from the manager, makes decisions, and sends the results to the manager. The speed with which this loop is made can be that of an algorithm, that does not stop until it finds the optimal solution, or that of a human who makes decisions step by step. The first non-optimal zone that contain values of the decision variables, that must be discarded because they cannot be optimum. From a human point of view, it contains decisions that should not be taken because there are better. The second, non-feasible zone, that contains values of the decision variables, that must be discarded because they cannot be feasible. From a human point of view, it contains decisions that cannot be taken because they are impossible. Decisions not included in the two zones determine the area of rationally desirable and possible decisions. The following table and image resume the study of behavior of GSDDP for a stochastic mixed linear economic electricity dispatch. The decrease in the solution time per scenario, when increase the number of scenarios, is a measure of the learning capacity of the GSDDP. Artificial hippocampus. Storing the history of runs. Following the principles developed by Benders, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. An expert system stores a set of cuts generated during a run for use in subsequent runs, which will produce a set of cuts brought from memory to transfer knowledge to the new run. High is researching the creation of methodologies to generate new rules, which adjust to the dynamic variation of parameters that affect cuts in the models. While all the mathematical support is solid, there is no theory that can indicate which cutting planes should be selected when restarting the model. Problem that becomes big when the size of the database grows. For this reason, it is considered necessary to develop tools, based on traditional artificial intelligence, artificial neural nets, to help the management of the hippocampus database. The idea is that for very large problems, the selection process will include an ANN. This is one of High's research projects. High is working on the use of convolutional neural networks to select the cutting planes to be extracted from the memory of the artificial hippocampus, to incorporate them into the mathematical problem whose solution algorithm is in a continuous learning process. Convolutional neural networks, CNNs, were designed for the processing of structured data, such as images, videos, and time series. They are based on the concept of convolution, which allows the network to learn important patterns and features in the input and output data. CNNs are widely used in pattern recognition tasks. An example of a CNN aimed at recognizing images of numbers written freehand is presented. In this case, the result is a discrete indicator associated with the number read. HNN assimilates the arrays of cutting planes that are in the memory of the hippocampus, and the arrays of the parameters of the problems to an image. This is true because images on a computer are stored in arrays of pixels. Both CNNs and the visual cortex have a hierarchical structure, with the simple features extracted in the first layers and the more complex features integrated into deeper layers. This allows for increasingly sophisticated representations of visual inputs. A CNN applies a set of convolutional filters to the input image, each filter triggering different features of the image, allowing for faster and more effective training. This filter concept can be extended to the output matrices, those of the cutting planes. Now, instead of images, we have input and output matrices, of cut planes, and exogenous parameters from past experiences, which are related to the input parameters of the new problem to be solved. One application of this approach is Imitator, a CNN that allows pre-trained models to recognize the conditions of the carbon mixture and the characteristics of the resulting carbon for a thermoelectric plant. As iterations occur, the number of connections in the artificial cortex increases, which corresponds to the learning of the algorithm, that is part of the artificial brain. If the dual variables of the subproblem of each iteration have been stored in the artificial hippocampus, when the process stops, and starts again, including the previous cutting planes, everything will be faster in the second run, implying that the brain has learned from one run to the next. The interested reader can consult the white paper. Artificial hippocampus: the energy of the artificial brain. An artificial intelligence without dynamic memory and automatic learning capacity, it can't be smart. Thank you for your attention.